Welcome back. In our previous videos, we explored concepts like arrival rate, service rate, and utilization. Today, we're diving into a crucial question for any system. At any given moment, how many requests are actually inside our system? This is more than just a number. It's a key metric for understanding system performance and resource usage. Whether requests are waiting in a queue or being processed, knowing this helps engineers make informed decisions about scaling and infrastructure. Every request in your system consumes resources. Think memory, worker threads, and database connections. If too many requests pile up, your system can slow down or even crash. That's why it's so important to estimate how many requests are present at any time. This knowledge lets engineers check if the current infrastructure is enough or if it's time to scale up. Instead of manually counting, we can use a simple, powerful equation from queuing theory. Queuing theory offers us Little's law, a straightforward equation to estimate the average number of requests in a system. Instead of tracking every single request, Little's law gives us a reliable way to calculate this number using just two pieces of information: the arrival rate and the average time a request spends in the system. This law is widely used in engineering to monitor and optimize system performance. Little's law is expressed as L equals lambda times W here. L stands for the average number of requests in the system. Lambda is the arrival rate, or how many requests come in per second. W is the average time each request spends in the system, including both waiting and processing. This simple formula helps engineers quickly estimate system load without complex monitoring tools. Let's clarify the variables. L is what we want to find, the average number of requests in the system. Lambda is how many requests arrive per second. W is the average time a request spends from entering to leaving the system. By understanding these variables, you can apply Little's law to any system, whether it's a web server, a database, or even a customer service line. Suppose your application has an average response time of 200 milliseconds, which is 0.2 seconds. This means, on average, each request spends 0.2 seconds in your system, from the moment it arrives until it's fully processed. This value will be our W in Little's law. Now, let's see how changing the arrival rate affects the number of requests inside the system. In the first scenario, your application receives 100 requests per second. Plugging these numbers into Little's law, L equals 100 times 0.2 equals 20. So, on average, there are 20 requests inside your system at any moment. This helps you understand how much load your system is handling under normal traffic conditions. Now, imagine your application becomes more popular and traffic increases to 500 requests per second. Using Little's law, L equals 500 times 0.2 equals 100. This means your system now has to handle 100 requests at any given time. Notice how a higher arrival rate directly increases the number of requests in the system, even though the response time remains the same. During a festival sale or a big event, your traffic might spike to 2,000 requests per second. Applying Little's law, L equals 2,000 times 0.2 equals 400. Now, your server must handle 400 concurrent requests. This scenario shows how quickly the number of requests can grow as your application becomes more popular or faces sudden traffic surges. Notice that in all these scenarios, the application code and response time didn't change. The only thing that changed was the arrival rate. Yet, the number of requests inside the system increased dramatically. This demonstrates how sensitive system load is to traffic changes and why monitoring arrival rates is so important for capacity planning. By using Little's law, engineers can estimate how many resources are needed to handle current and future traffic. If the number of requests grows, you might need more memory, threads, or database connections. This proactive approach helps prevent slowdowns and outages, ensuring a smooth user experience even during peak times. Little's law isn't just theoretical, it's practical. When you see the number of requests rising, you can decide whether to scale your infrastructure. This might mean adding more servers, increasing database capacity, or optimizing code to reduce response time. Little's law gives you a clear, data-driven way to make these decisions. While we focused on web applications, Little's law applies to many systems, like customer service queues, manufacturing lines, or even hospital emergency rooms. Anywhere you have arrivals, processing, and departures, Little's law can help you understand and optimize the flow. It's important to remember that Little's law assumes the system is stable and the averages are meaningful. If your system is overloaded or traffic is highly unpredictable, the results may not be accurate. Still, for most practical cases, it's a reliable tool for estimation and planning. To wrap up, Little's law is a simple yet powerful equation that helps engineers estimate the average number of requests in a system. By knowing the arrival rate and average time in the system, you can plan resources, scale efficiently, and ensure a smooth experience for users. Keep this tool in your engineering toolkit for better system management.